Good morning, everyone. It is around 7 a.m. in California. So in this clip, I will discuss about the basic introduction of buck converter. Here's your basic diagram of a buck converter. It is very simple. We have three major components. The FET, which is acting like a switch. It will turn on and off at high frequency. And we have the diode. After that, we have an L and a C. The L will limiting the rate of current, and combination of LC will filtering out the pulse voltage input and creating a DC voltage output. Here's your source, which is a load, and your input is a DC voltage. The most important of the buck converter is that your input voltage always has to be higher than your output voltage. This is one of the most important converter that for beginner that you need to learn this one carefully. Here are some of the advantage and disadvantage of the buck converter. For advantage, the converter can run at high frequency. Normally 100 kHz is one of the best option, but you can start out at low frequency, 10 kHz or 20 kHz. The size, the higher the frequency, the smaller the size of the power components. In this case, the inductor and capacitor size. The circuit is simple. As you can see, it doesn't involve with a lot of components. For efficiency, it can achieve very high efficiency, more than 90%. Some can get up to 95 or even 97%. Depends on your voltage and current. For the outputs, you can design a constant voltage or constant current. Depends on how you use your control circuit. For disadvantage, the buck converter is a non-isolation between the input source and the output source. So what it means is that when a FET is shorted, the output will see whatever the input voltage is, which is dangerous. That could damage your output load. The output of the buck converter only has one output. That's one of the disadvantages if you want to design for multiple output. Another point, which is all switch mode power supply will having this kind of communication, the feedback control system. Basically, we can split into two different types of control circuit. We call a voltage mode control and current mode control. Here is the basic operation of a buck converter. Supposedly, we want to design a 12 volt DC output, and our input source is 24 volt. So the buck converter is suitable for this design. And we're combining with 4 power components: the FET, the diodes, inductor, and capacitor. So the FET will turn on and off at high frequency. And your output voltage, the equation is very simple, related to your input based on the duty cycle. Duty cycle is the time or the rate of open of your FET. So supposedly, if we have an output of 12 volt and the input of 24 volt, and the efficiency of the buck converter is 90%. So our duty cycle will be VR divide by V in, multiply for efficiency. So your duty cycle will be 0.55 in this case. So duty cycle is the time you turn on, or the rate when you're turning on the FET. Here is the basic operation of the buck converter. There are two different modes. We have a FET turn on mode and we have FET turn off mode. So in the turn on mode, the source Vin will supply current to the output through the inductor, and some ripple current will go through the capacitor to filtering it out. The inductor will control the rate of change, slow down the rate of change of the current. So in the off state, when the FET turning off, the energy stored in the inductor will flow from the bottom diode, we call a catching diode, to L, and some ripple current to capacitor. Most of the DC current will go through the output load. So those are the two stage of operation in the buck converter. So how do we design the inductor L and the output capacitor C? This is the most important parts of the power converter. So these are the parameters that you need to know. Fs, which is the switching frequency of the converter, and is the efficiency of the converter. Normally we choose around 90% for the buck converter to make it easy. Delta IL, which is the ripple current, the peak-to-peak ripple current through the inductor. And delta VC is the ripple voltage of the output. Also the same ripple voltage across the output capacitor. VG is the input voltage and VO is the output voltage. Another parameter which is related to Fs. Let's say if we have T is a switching pairs, and the equation is 1 over F. If you have 100 kHz and your period, which is the time for each cycle, is 1 divided by 100,000. So that is 10 microseconds for each period. Now your basic equation for duty cycle is VR divided by input voltage and multiply for efficiency. There are two most important equations that in the power converter. The first one is the IC. The IC is the amount of current charging into capacitor equal to C time for dV and divided by dt. For VL, which is the inductor voltage across the inductor, is L time for dI divided by dt. So let's skip the detail, the complex of that. From those equations, they come up with two equations to design for L and C. L is the Vg minus Vo time for D divided by Fs and multiply for ripple current. For C, it is the ripple current divided by 8 time for Fs, which is the frequency, and multiply for the ripple voltage. So very straightforward. Let's go into an example of design L and C, the value for L and C. So in this case, we have a switching frequency at 100 kHz. We have the input is 24 volt with the output of 12 volt. So our T will be 10 microseconds. The duty cycle is 12 volt divided by 24 and multiply for 0.9. So our duty cycle in this case is 0.55. Or if you multiply that 0.55 for 10 microseconds. It means that the turn on time for each cycle is 5.5 microseconds. Now our next step is to pick the ripple current and ripple voltage. Normally people design the inductor or ripple voltage between 10% to 20% compared to the load current or the load voltage. So in this case, I choose 10% of the load current. If my load current is 5 amp, so my ripple current will be 0.5 amp. And for a ripple voltage, if I choose 10%, so if I take that and multiply for 12 volt, so my ripple voltage will be 0.12 volt. So those are the two parameters that you need to design. Where do you want to design for that? The ripple voltage is important. Some of them could getting down to 5%. Depends on the requirements of the circuit. So from those, I will calculate for my L. And the result is 132 microhenry. And for C, I will get 5.2 microfarad. So those are the two basic things that you need to come up when you want to design for a buck converter, which is the most important part of the circuit. I will not getting into the detail of ESR in the maybe latest clip. We'll discuss more detail of that. The ESR is the internal resistance of the output capacitor, which will impact the ripple voltage. So basically in this case, you won't get 0.12 volt. There would be some ripple current goes through the capacitor and multiply that with the ESR. So that will increase your output ripple voltage. This is one of the example, and the components, the IC components is the LM2596 if you're using the version -5. So all you need to do is that getting this IC and with only a few components, 1, 2, 3, and 4. The C is the input, which is the filtering the ripple current that kick back into the source. And you can design a buck converter based on this IC. But the output load current of this converter is limited to 3 amp only. And here's one of the sample that you can buy it from Amazon or eBay. From eBay, you can buy it for only $1. So if you don't want to spend time for design, you can buy one and test it out. So this is the end of my clip about the buck converter, and I hope you learned something. Thank you for watching. Please comment, subscribe, and like to motivate my work. And we'll see you in next clip.